Welcome to the first installment in my series, Programming a 6502 Assembler in 6502 Assembly Language. As I said in the introduction, which would be episode 0, I guess, the goal today is to look at the command line and to be able to extract the command line arguments. As part of that, I also write some code to output information to the screen so that I can debug. Well, we'll need that later for the assembler anyway, but it'll be useful for me for my debugging. So here I am, I just rebooted the emulated computer. So let me set the prefix to O. And if I do that, you see I have orca.system, which I can run. And then make sure my prefix is set to AOS, which is the working directory I'm going to use to make the assembler. Now, it's empty, as you can see, so I'm starting from scratch. So the first thing I'll do is start a new file. Okay, and the first thing I have to do is I have to tell this Orca assembler what the name of my object file should be. So I'll just call it WSAS. I also want to turn off the listing so that when I assemble a program, it doesn't try to generate a listing. I will also, turn off the symbol table because I don't want it to print out a symbol table for every part of the program when I assemble it, because that's just kind of a waste of time for me. Okay, so at this point, I'm just going to save the file and then go back. All right, in the Orca assembler, you organize your code in code segments and data segments. And these are really not the same thing as the text segment and data segment that you would see in more modern systems or that I want to have in my assembler. It's really just a way to organize your code so that you have your global labels and your local labels. And when you're finished, when the assembler is finished assembling a given code segment, it can throw away all the local labels and clear out the symbol table a little bit. So I'll start here with the code segment called main, and with start and end. So everything between this start and this end is in the main code, the code segment called main. All right, and any labels in here that aren't specifically specified as entry points will be local labels. All right, like I said, the first thing I do is write some output routines because I want to be able to debug. I'm going to need to be able to debug my code, so I'll need some output routines for that. So I'll start with a putC routine. This will just output a character to the screen, or as you'll see in just a moment, it can actually be output somewhere else, but generally it will be to the screen. And this is going to be an entry point. In other words, this is not a local label. We want this to be accessible everywhere. In the Apple II, there is what's called an output hook at locations 36 and 37 hexadecimal in the 0 page. And what this is a pointer to a routine which will output the character, which is an accumulator. Normally it outputs it to the screen, but you can change the hook to point somewhere else and it will do whatever you want to with the character. You can even put your own routine in there if you want. But typically, Apple II programs will send characters they want to output to the output hook. And so I will do that also. Okay, so when I put a character, what I want to do is first off, again, for the Apple II, when you're outputting to the screen, you need to set the high bit of the ASCII character that you're outputting. If you don't set the high bit, it will come out as inverse or flashing or some horrible thing that I don't want. So let me just go ahead and set the high bit. And then, jump to the output hook. All right, so when someone calls the putC routine, then the putc routine will set the high bit and jump to the output hook, which will output it. When the code that is pointed to by the output hook returns, then we'll return to the caller of putc. All right, well, that in itself would work right there, but I want to do a few more things. First off, I intend to use the ASCII new line character, which is ASCII 10, to specify that I want to print a new line, just like you would do in Unix. But in the Apple II, it's normal that the carriage return character, that is ASCII 13, is used for the same purpose. So what I have to do here is take the character which is in the accumulator and compare it to the new line character. If it's not the new line character, I can just go ahead down here and, you know, set the high bit and put it out. Otherwise, I'm just going to load the carriage return character. So if I'm calling putc and asking it to output a new line, it will just change that to a carriage return before it goes to the output hook. That way it will work the way that I expect. And this also gives me the possibility here to put another entry point called NL. So if I do a JSR to NL, it'll just, you know, put out a new line. Basically, it'll cause a carriage return to the next line and put out a new line. So it's just an easy way to go to the next line when I'm printing things. All right, so that looks pretty good to me. The next thing I want to do is I want to be able to print out numbers. And decimal numbers are kind of a pain. So I'm just going to worry about hexadecimal numbers right at the moment. So I'll make a little subroutine called putxt for put hex digit. I don't think this needs to be an entry point. It can be local to the main segment. So instead, what I'll do is I would just, this is going to be just a 1 hexadecimal digit, and it's going to be stored in the accumulator. So first I'll make sure it's just 1 hexadecimal digit by clearing the 4 high bits of the accumulator. And now I need to compare it to 10. If the value is less than 10, then I'm just going to add an ASCII 0 to it and output it by jumping to putc. Okay. If the value of in the accumulator is greater than or equal to ASCII 10, then it's going to be printed as hex digit A, B, C, D, E, F. Hex digit A is ASCII 65. Hex digit 0 is ASCII 48. So what I'm going to do is say I want to put out, if for example, if there's a 10, I want to change this 10 to a 65. By adding 0 to it, I'm adding 48, which makes it 58. Okay, and also if I put an ADC here, I'm adding the carry in, but that makes it 59. So in order to get a 65, which is what I want, I have to add 6. So if I have ASCII 9, for example, if I have a 9 here, that is to say, it's less than 10, it'll go down here and add 9 to the ASCII 0, which will give me an ASCII 9 and print it. If I have an ASCII 10, or if I have a number 10, then it will not go down there. It will go here instead. It will add 6 plus 1, the carry, because carry is set here, to 7, and make it a 17. Then add ASCII 0, which is a 48. 17 plus 48 is 65, which would be an A, which is what I want. All right. Now, I'm going to use that routine in this one, which will print a hexadecimal byte. And this will be an entry point. All right, here what I'm going to do is I'm going to push that accumulator onto the stack. Then shift it down 4 bits so that the high nibble is being printed. Now I'm going to get it back off the stack and print the load nibble. All right, that looks pretty good. The last thing I want to do is I want to be able to print a string. So I'm going to make a little puts routine, which will also be an entry point. All right, so what I like to do for my puts routine is I like to have a pointer to a null terminated string passed in the X and Y registers, and then it prints that out. And I'm going to use some self-modifying code here to make this easy on myself. So what I'm going to do here is store this into, let's call it puts 1 plus 1, and store y into puts 1 plus 2. And then here I have puts 1 and, all right. So what's going on here is that the pointer to the string is going to be stored right here in place of this FFFF. And then I'm going to use the X register to index the string and get each individual character and print it out. And to do that, I need to have here I'm going to have here load X with 0. So 0 is going to be the index. So as I come into this, I'm going to store my pointer here. I'm going to load X with 0, and then get the 0th character in the string. I'm going to then print that. Okay. And now what I'm going to do is increment. Oh, actually, what I need to do is get the 0th character in the string. If it is a null byte, I have to break the loop. So once I get a null byte, I'm not going to print that. If it is anything besides a null byte, I will print it. Then I'm going to increment this byte right here. Increment this thing right here. Okay? And also check for that to become 0. If this were to become 0 after being incremented, that means that I've wrapped all the way around. This number has gone all the way up to 255 and then was incremented one more time and became 0. So if it's not 0, then I'll branch to put 0, which means I'll go ahead and load the newly incremented value into X, and that means I'll get the next character in the string and print it out. Okay, and here is where I'm done. So if I get a null byte, I'll come down here because I'm done. If my string is 256 bytes long or more, so that I increment put 0 plus 1, this byte right here, and it wraps around to 0, then I'll also be done. And so we'll just return there. All right, let's just take a quick look at this stuff before I continue. So I have a character in A, I compare it to 10. If it's not a 10, I set the high bit and print it. If it is a 10, I throw it away and get a character return character anyway instead, set the high bit and print it. And I can enter here just to print out a new line if I need to. All right, so for the puts, I come in with a pointer to the string in X and Y. I put them here, I put the pointer here. I get a 0. I'm going to load the character in the string here. If it's null, I'll go down here. If not, I'll print the character. Then I'll increment this byte. As long as that doesn't wrap around to 0, I'm going to go back up and do this again. There's a problem here though. Like when I exit this routine, I have to reset this thing here to 0. That's absolutely necessary. So if I get a null byte here, I can just store that null byte there. So like right at this point, I load the character in the string, it's a null byte, and go down here, I can just store that right here to reset this to 0. Otherwise, next time I call it, this will not be a 0 and everything will be all screwed up. Because whenever I enter this routine, this had better be 0. So I've put a 0 there, and then I return. Now, if I have a string which is so long that I don't branch here, then I need to go ahead and make sure there's a 0 in the accumulator before I do this. So if I were trying to print out a string which is 256 bytes in length or something like that, then this increment here would wrap around to 0, and this branch would not occur. I would come down here, but I don't have a 0 in the accumulator, so I have to go ahead and load a 0 into the accumulator before I store it here. So that looks good. Okay, that's good. I'm glad I caught that little problem. All right, so now if I'm going to print a hexadecimal digits, first off, make sure that what's in the accumulator is actually printable as a hexadecimal digit, that is from the range from 0 to 15, by doing this right here. Now I see if it's less than 10, I'm going to go down here, just add an ASCII 0 and print it out and be done. If it is 10 or greater, then I have to add a 6, but because Carrie said it's actually adding a 7, right? So for example, 10 will become 17, then add 48. 17 plus 40 is 65, so I'll print in an A. That's exactly what I want. Now for print hexadecimal byte, first I save the byte I'm going to print out. Then I move the high nibble down to the low part. I print that out. Then I retrieve the byte that I got, and I print out the low nibble. Right, and of course it's going to it will print out correctly because of this right here. All right, that all looks good. So what I want to do now is just a little testing. All right, so let's try printing out an @ sign. I'll do a new line. And try printing out A5. Okay. And another new line. That's X. This is going to be a string here. Puts, return. I need to make my string. Hello world seems like an appropriate thing to say. All right, so I have hello world followed by a new line and then a null byte. All right, let's hope it assembles. Save, exit, assemble and link. Oh, did I forget to change the label? Okay, that was a dumb mistake. That's supposed to be equal to 36. Right, and this is supposed to be put xt0. Okay, save it. All right, and let's see. Nice, that looks good to me. All right, so we have that stuff out of the way that was helpful for debugging. So let's get rid of this. All right, so now I'm actually ready to start working on the main goal of today's installment, which is to look at the command line. And I have here the documentation for the Orca environment, and it says that right before calling your program, the address of the command line is placed in 0-page locations 2 and 3, and the string is a sequence of ASCII characters ending with a return character. So I need to, let's call it command line pointer is at 0-page locations 2 and 3. Okay, so now, what I want to do, I can get rid of this also. I'm going to put my data down here. I'm going to have here argc, which is going to be 1 byte. And argv, which is going to be an array of pointers to each of the individual command line arguments, or whatever is on the command line. And I'm going to allow, right now, I mean, probably 8 would be enough, but let's just go ahead and make it 16 command line arguments. And since I'm going to have a pointer for each one and pointers are 2 bytes, I need 32 bytes here. Okay? So 32 bytes will allow us 16 command line arguments. All right, and here we will start. Okay, so first I'm going to initialize x and y with 0. Now y is going to be my index into the command line. And x is going to be an index into argv. Okay, and the first thing I want to do is I want to, basically the idea is this. I'm looking at the beginning of the command line, and I'm just going to assume that there could possibly be blank space there. So I'm going to skip over any spaces until I find a non-space character. All right, and let me just think of a nice label for this. Let's call it getCL for get command line. All right, so I'm going to get a character from the command line, and if it is not a space, I'm sorry, I have to compare it first to a space. If it's not a space, I'm going to bail out of this. Here, I just call this getCL0 for whatever reason. Okay. So getCL1 is going to exit this loop. If it is, okay, if it's not a space, I'm going to exit the loop. If it is a space, I'll increment y and go back to the beginning of this loop. All right, now, because I'm using this Orca command line environment, I feel extremely confident that the command line that is given to me will always end with a return character, and it will be less than 256 bytes long. So I don't really have to worry about what happens if I run off the end of the command line. So I really think it's not possible for this branch to not branch. That means it will always go back up here. The only way in which it could not go back up here is if y became 0, but y would only become 0 if the command line is at least 256 bytes long. But the Orca command line environment is not going to allow me to do that, and it's not going to allow the command line to be that long, I don't think. So I really just don't have to worry about it. So I'm not going to worry about it. I'm just going to assume that I don't have to worry about this. All right. So this is the situation where I have a space, or I'm sorry, I have something which is not a space. First off, I just want to see if it is the carriage return at the end. If it is, then I need to go to, like, I know, .cr. No, maybe not that. Let's say ncl. If I get that, it's the end of the command line. All right? Otherwise, y, my y register here, is indexing the beginning of an actual command line argument because I've just skipped all the white space. So what I need to do here is actually build a pointer to the beginning of this command line argument. And I can do that by, first off, clearing carry just to make sure it's good. Put Y in A register and add CL pointer. I'm going to store that in argvx. Remember, x is 0 up here, so the first time I go through, I'm going to store it into the, this is the low byte of the pointer to my command line argument, and I'm going to be storing in the low byte area here. Now I'll have to increment x, and now get a 0 in A, add, complete this 16-bit addition by adding the high byte in. This is just to manage a carry from this addition here. And we'll store that in there and do that. Okay, I got a phone call there I had to answer. So let's continue. Where was I? So this part is getting the, skipping the spaces. And here I'm building my pointer. Okay. All right. So that looks good. I built my pointer. Now I need to get to the end of this command line argument that I have. So let's call this get CL2 and Y. So when I finish this one, I've skipped spaces and Y is looking at the first non-space. Okay, and so when this load here is going to get that same character. Nothing's really changed here yet. So, all right. So now, if this is a space, I'm going to exit. All right. And if it is a carriage return, I'm going to exit. But this is going to be a different exit here. And the reason for that is that after I get a space here, I'm going to go back up to the top and start skipping spaces again here. But if I get a carriage return, then I'm done. So I'm going to go to a different place. All right? So increment Y. And just like I said before, this should always branch, because the only way it could not branch is if I haven't found a carriage return, but I've already found 256 characters in the command line. That's not like that. I think Orca doesn't allow that to happen. So that would be an always branch, basically. Okay, at this point, now I have found a space. And what I need to do here is, first off, I'll go ahead and increment argc, because I've gotten into this command line argument. It seems to be valid. Everything looks great, so I'm going to increment argc. And then I'm going to, I need to replace this space with a null, because I want all of my arguments to be null terminated. So I can just load 0. So I'm replacing that space with a null. Okay, and now I'm going to increment Y to get past that space, and that might very well already be the next command line argument if there were only one space between the two, but I don't know. And again, this should be an always, a branch always situation. And it's going to branch right up, back up here to try to skip spaces again. Okay. So that's going to go to get CL0. All right. So get CL4. This is the case where a command line argument ended with a carriage return. Okay. So it's basically the same thing here as the case of get CL3, but the difference is that I just don't want to branch back up there. So I'm going to go ahead and increment the argc. I'm going to null terminate the command line argument. And now I'm not going to branch back up there. I'm all done, basically. I don't need to increment y. And now let's go back up and think about this situation where I'm up here and I'm scanning through spaces and I get a carriage return that goes to NCL. So that would be right here. Yeah, this is where I'm all done. Okay. So at this point, I should be all done. And for the moment, I'm going to put here A and OP, assembler no op. It's just a pseudo operation that for this assembler means I want to label with nothing else on the line. Okay, so let's try something here. What I'm going to try first is just try loading the argc and printing it. All right, and quit. So if all this works, then I should have the number of arguments here in argc. And of course, I should also have the pointers to each individual command line argument, but for the moment, I'm just gonna print out the argc and see if that works. So quit, save, exit. Oh, BEG is not. All right. I can search like this. There we go. This is actually supposed to be Q, right? Okay. All right, now let's see. Does say T1, T2, T3, and it gives me 3. That looks very nice. All right, so let's go back here and see if I can print out all the command line arguments. All right, so I print out the number of command line arguments, that is the argc. And now what I want to do is, this is of course just debugging code here. So let's call it put CL. And oh, I know what I'll do. I'm just going to do another kind of self-modifying code thing like I did before. All right, I'm going to start with 0, compare to argc. If it's equal, that means I'm done. Okay, and that'll be called what? Put CL2. All right, if we're not done, then I'm going to shift it to the left as multiply times 2. And I'm going to put that in X. And I'll get RV plus 1 X. This is the high byte of the pointer to the command line argument. And I'll store that in Y. And the low byte of the pointer to the command line argument will go into X. And I will print it out. Okay. And now I will increment put CL. That's incrementing put CL plus 1. I'm incrementing this byte right here. Okay, and good. All right, and I'll just call this put CL0. Okay, and that will be done. So I print the number of command arguments and a new line. This will be this is counting up the command line arguments. Start with 0, 1, 2, 3. When it gets to argc, it's done. It multiplies it by 2, puts into X, and uses that to access the pointer to the command line argument from the vector, and prints it out. and then puts a new line. Increment this counter, and then branch back up here. That all looks good. There's just one small thing. I think I want to put the command line arguments between some sort of brackets just to make sure that there's no spaces or anything that I won't be able to see when it's printed out. So to do that, I think maybe right here, I'll go ahead and push that. I'll load the left bracket, print that out. All right, then I'll get A back, then shift it, blah, blah, blah. Okay, and then right here, I'll load a right bracket and print it out. Okay, and here I don't have to push A and pull A because I don't care about the value of A. It doesn't matter to me if it's destroyed. Whereas up here I do care because it's the current argument count. All right. All right. Let's assemble that. Oh, yeah. This assembler demands that I put ASLA here. All right. That looks very nice. Put some spaces in there. More. I don't know, true, and some spaces in the end, and hit enter. That looks very nice. All right, so I'm going to call that done for this installment. We have successfully looked through the command line argument string and pulled out each of the individual command line arguments and put them in an argv vector, and we have an argc which tells us how many there are. So that's all for this installment, and I'll see you next time. In the next installment, I will be writing some code to abstract away from the operating system. I basically want to write code that will allow us to create a file, open a file, close a file, read a file, write a file, maybe seek. But I want to kind of abstract away from the Apple II specific way of doing that, and also just do it in a way which, to me, feels a little bit more comfortable. And you'll see next time why I don't particularly love the way that it's done on the Apple II normally. So anyway, that will be the next installment. So I will see you then.